So, what we really need to do in order to look for Earth-like planets is direct imaging of exoplanets. So let me get a quick pointer. I think I've got one over here. Wave it around. Okay. So these are a couple of images that have come out relatively recently of new techniques which have allowed us to see exoplanets directly. We now know of thousands of them out there, but virtually all of them have been seen by what we call indirect means, where you look at the radial velocity oscillations of a star through its Doppler shift because it's moving around the center of mass with something much smaller, or transits, as in the Kepler experiment, where you see a slight dip in the brightness of the star. You're not really seeing the planet, you're seeing the effects on the starlight. To find out if they're Earth-like planets, we've got to do direct observations of the planet and separate that radiation from the planet from the starlight. Okay, and here are two very interesting ones. This is an image taken with the Hubble Space Telescope of a debris disk. It's like the asteroid belt on steroids. It's actually more like the Kuiper belt on steroids. It's way, way out and very, very cold around this second magnitude F star. And then Hubble has a little speck in the focal plane where you can put a black dot and get rid of most of the starlight, and you can see this ring. Then a couple of years ago, right about here, somebody saw a bright spot, and then a couple of years later it moved over here at just the right speed, but then a couple of years later it was gone again. And so there might have been a planet, or maybe it was just a bright clump of stuff, or maybe it was an error in observing, but we may have seen a planet out there in the ring around Fomalhaut. This stuff's done on the ground with large telescopes. You have a very bright star and a coronagraph that is moving rapidly to take out the effects of the atmosphere. And on this HR 8799, 3 planets have become visible. It's really quite astonishing that you can do that at all. But these planets are down at about 10 to the minus 4 the brightness of the central star. So they're 1/100%. We want to see Earth-like planets, we're going to have to go 1,000,000 times deeper in contrast. So if there were an Earth around here, first of all, it would be seated right about there. And second of all, it would be 1,000,000 times fainter than these guys. So that's a tough problem to be able to find Earths. Okay, we got a lot of people all over the country, and some in Europe as well, interested in participating. I won't dwell on that. And this is a chart I used to just show how difficult it is. That's just a regular picture with a good telescope of the star Regulus. You see diffraction spikes and you see scattering. Scattering way, way out at the edge. It's just really going to be tough to see an Earth, because it would be 1 Hubble pixel away from the central thing and 10 billion times fainter. So millions of times fainter than these faint stars out here, right there in the middle. So JPL worked on something called the Terrestrial Planet Finder for the better part of a decade. And they came up with a design that was so difficult that when the price tag started wafting north of $10 billion, it got canceled. So when I wrote this, NASA's not been good to it. Now it's gone. And it's come back under my name of New Worlds. That's another story. Anyway, first they looked at giant interferometers, an array of 8 or so 30-meter cryogenically cooled telescopes flying with beam stability good to nanometers across hundreds of meters of space. Not easy. then there was, oh, if we need a perfect image, let's just build a perfect telescope. Planet light and the starlight come in, reflect over here, and then you stop the starlight and let the planet light through, much like that Hubble image. Well, that turns out you have to make this unbelievably tough. Close to an 8-meter telescope with surface, so kind of close to the area of this room, or at least half this room, where every atom on the surface is in position to its own diameter. And then some years ago came up with the concept of an external occulter, and it's a really old idea. But the problem was, so the idea was just keep the starlight out of the telescope and let the planet light in by putting an occulting object between your star and your telescope and look for exoplanets over the limb. That way this 10 billion photons just never gets in the telescope at all, and yet all of the light from the exoplanet. Now, of course, this is a very small angle. I'm showing it there at about 15 degrees away. But actually, you want this to be 1/10 of an arcsecond in angle. So this is actually very, very far away from this. And if you can build a device that shadows this well enough, then you can get rid of the starlight and still see the planet light, and that's the idea. So here we have a 50-meter diameter star shade throwing a shadow. This represents the dark spot, represents the 50-meter shadow. And you literally fly a space telescope from Hubble class into the shadow and look at this back at the star. So here I've got a little animation of a bright star, fainter stars in the field around it, and then when your star shade goes into position, it blots out the star, and hopefully you see a little cluster of starlight, very faint star-like objects left, which are the planets. That's the concept.